The transmission crackles. A Mosquito pilot's voice, steady, almost casual. "Control, we've got bandits. 2 FW-190s at 5 o'clock, climbing." There's no panic. No scramble. Just the sound of twin Merlin engines climbing at a pitch that shouldn't be possible. Below, the German fighters struggle to keep up. In the cockpit, the pilot doesn't think about what's happening behind his fuselage. He doesn't know about the hands that tuned those engines. Doesn't know about the man who adjusted fuel jets in the dark, who bent rules written in blood, who believed that bureaucracy was a slower killer than any cannon shell. All he knows is that his aircraft is fast enough to go home. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Up ahead, RAF Marham. On the ground, a single maintenance hangar, oil-streaked concrete, the smell of high-octane fuel and metal shavings. In that hangar, an engine fitter named Roderick Banks just watched the same Mosquito land. He doesn't wave. He doesn't celebrate. He simply walks toward the aircraft, torch in hand, and begins his inspection. He's looking for stress marks, for detonation carbon, for the signatures of what he's done. The modifications were illegal. The speed was impossible. The pilots, the ones who knew, called it Banks magic. But magic is just physics that nobody understands yet. If this history matters to you, tap like and subscribe. RAF Marham sits low in Norfolk, England, where the North Sea wind never quite stops. It's early 1942. The war has ground into a new shape. Fighter sweeps over France have failed. Daylight bombing has become a calculated slaughter. Somewhere in the Air Ministry's corridors, they realized that velocity was the only defense that mattered. Speed meant survival. Speed meant home. The de Havilland Mosquito had just entered service 6 months before. It was revolutionary, a medium bomber built from wood when all the metal was needed elsewhere. Designed by R.E. Bishop in 1938 as a fast, unarmed day bomber, it was almost laughed out of existence by Air Ministry brass who believed that bombers needed turrets, defensive armament, protection. Geoffrey de Havilland overruled them. His design was simpler. Make it so fast that nothing could catch it. At 380 miles per hour, the Mosquito was the quickest aircraft in the RAF when it arrived. Nothing else came close. Pilots fell in love with it the moment they strapped in. The cockpit was roomy, like a lounge chair, one pilot said. The view was exceptional. The feel was alive. For the first time in the war, British airmen had something that could go anywhere and come back. Except the Germans adapted. By late 1942, new Focke-Wulf FW-190s and Messerschmitt Bf-109GS began appearing over France and Germany. Fast, disciplined, and crucially, they could catch a standard Mosquito if the Mosquito was weighed down with bombs, or if the Mosquito pilot miscalculated altitude or entry angle. The tactical equation, which had seemed solved, fractured again. Pilots began returning with stories. The FW-190 was faster in a shallow climb. The 109G outran them at altitude. The margin of safety that had felt infinite in 1942 became a knife's edge by 1943. In mission debriefs, commanders heard the same refrain: "They're catching us. We need more speed." The Air Ministry's answer was bureaucratic. Wait for the next variant. Wait for the new Merlin 61 engines with 2-stage supercharging. Wait for the improved propellers. Wait meant months. Wait meant more aircraft lost. Wait meant pilots going into that cockpit knowing the numbers weren't in their favor. But the RAF couldn't say that. So they nodded and filed reports and promised that solutions were coming. In the maintenance hangars, nobody waited. RAF Marham was one of 7 maintenance units serving Mosquito squadrons. It was commanded by a station engineering officer who understood that theory and practice lived in different worlds. Roderick Banks was a sergeant fitter, an engine specialist who had started as a Rolls-Royce apprentice before the war. He had joined the RAF in 1940 when Hitler seemed inevitable and skill was the only hedge against oblivion. He was 32 years old. He had the bearing of someone who did not talk much, but whose hands were never wrong. Banks knew the Merlin engine the way a musician knows an instrument. The engine had tolerances, specifications stamped on documents by Rolls-Royce engineers, approved by Air Ministry officials, set in stone. Or so everyone believed. But Banks had spent 3 years in Rolls-Royce's development shops before the war. He had rebuilt thousands of engines. He understood that tolerances are not walls. They are thresholds. They define the space where a machine can operate safely, predictably, within the margins that engineers calculated for worst-case conditions. But what if worst-case conditions never happened? The Merlin's boost pressure, the amount of air and fuel mixture forced into the cylinders, was officially restricted by the Air Ministry to protect engine longevity. If an engine lasted 200 hours at full boost, Whitehall reasoned, then pilots needed to preserve those 200 hours across dozens of missions. Save the engines. Save the war machine. The arithmetic was bureaucratic and logical and completely separated from the fact that if your aircraft got shot down on your fifth mission, the remaining 195 hours meant nothing. Banks believed that boost settings could be adjusted safely for limited periods. He believed that the Merlin could handle 2 or 3 additional pounds of boost pressure for an hour or two without catastrophic failure. He believed in mathematics over doctrine, and so he began testing. The work happened at night, in a locked maintenance bay at RAF Marham, after the day shift had cleared out and the duty officer looked the other way. Banks brought a single Merlin engine, one that had reached the end of its service life anyway, and began systematic adjustments. He modified the fuel jet to allow a richer mixture. He altered the boost control mechanism to permit higher manifold pressure. He consulted his personal notes, calculations he'd made at Rolls-Royce, curves he'd memorized from engineering handbooks. He ran the engine on a test stand, monitoring fuel flow, cylinder head temperature, detonation limits. He pushed the boost up 1 pound, then 2, then 3. The engine held. His gauges showed acceptable margins. His calculations confirmed his intuition. The stress on the pistons, while higher than design specs, remained within what the titanium and steel could withstand for short bursts. If the engine failed, if it catastrophically detonated, if metal fragments came apart at high speed, it could be explained. An old engine reaching the end of its life. A fitter's miscalculation. An accident. A regrettable incident. Nobody would need to know it was anything else. Roderick Banks was not a pilot. He was not a figure who sought medals or recognition. His voice was quiet. His movements economical. He did not drink much or tell stories in the officers' club. Men described him later as methodical, exact, reluctant to speak unless he had something definite to say. He was born in 1910 in England, during the reign of King Edward VII, when flying was still an event that drew crowds. His father took him to Reims in 1909 to see Henry Farman fly a biplane in a circle for the first time. Young Rod Banks was 5 years old. He stood in the crowd, grease-stained and wide-eyed, and watched a man in goggles and a cap coax wood and wire into the sky. Something in him, some electrical connection between hand and logic and the visible physics of flight, crystallized that day. He never thought about being a pilot. He knew, with the certainty of a boy who understands his own mind, that he belonged on the ground, working with machines. By the 1920s, as aviation became less miraculous and more engineering, Banks was apprenticed to Rolls-Royce. The company was building the Merlin engine specifically for the Supermarine Spitfire, but the Merlin was being installed in everything: bombers, reconnaissance aircraft, trainers. Banks learned the engine not just by rote, not from drawings, but by disassembly and analysis. He understood how the fuel injectors atomized. He understood the geometry of the combustion chambers. He understood that an engine is a conversation between iron, air, and fire, and that conversation is governed by the laws of thermodynamics and compression ratios, not by the opinion of desk officers. When war came in 1939, Banks was 29. He volunteered for the RAF as a civilian engineer, then formalized it into a commission as an engine specialist. He was stationed at various maintenance units, following the squadrons, becoming a quiet reputation among ground crews. Pilots didn't know his name, usually, but their engine fitters did. A Mosquito that had passed through Banks' maintenance bay would start quicker, climb stronger, cruise easier. No one could quite say how. It wasn't sabotage, wasn't shoddy work. It was just better than specification. By 1942, Banks was at RAF Marham, assigned to No. 105 Squadron, one of the first Mosquito units. He watched the new pilots arrive in their aircraft. He heard the debriefs about German fighters catching them. He felt the mathematical wrongness of the situation. The Mosquito was designed to be faster than anything. Faster than fighters. Faster than fate. If it was slowing down, if it was becoming catchable, then the problem was not the aircraft. The problem was that no one was asking the machine what it was truly capable of. Banks had tried the official channels first. He had filed a report suggesting that boost pressure could be increased safely during combat operations. The report was filed. Nothing happened. He had spoken to the flight engineer officer. He was thanked for his diligence and told that such matters were handled by Rolls-Royce. He was told that doctrine existed for a reason. He was told, with the kind voice of authority explaining obvious truths to someone too junior to understand, that the Merlin's limitations were established by brilliant engineers in a well-equipped facility, not by a fitter at a maintenance unit. Banks said nothing, but he didn't accept it. What he did was build a hypothesis and test it. That is what engineers do. They observe nature. They construct a model. They experiment. They document results. They refine. They do not petition authority for permission to understand better. One engine, night work, systematic adjustment, documentation only in his private notebook, in shorthand that no one else would understand. The modifications took weeks to complete. The engine passed every test he could devise. The boost control mechanism he altered was reversible. It could be returned to standard settings in minutes if an inspection threatened discovery. When he was satisfied, Banks requested a meeting with the squadron commander, Wing Commander Peter Channer. Channer was a pilot, not a bureaucrat. He had combat experience. He understood that rules were written by people sitting in offices far from the guns. Banks explained what he had done. He showed the test data. He explained the physics. He said that the modifications were safe for limited periods and would provide a meaningful increase in speed, enough to alter engagement geometry, enough to allow an aircraft to disengage from a pursuit it couldn't outrun. Channer understood immediately. He also understood that official approval was impossible. The Air Ministry would never sanction illegal modifications. Rolls-Royce would never certify work done outside their plants. The RAF's chain of command would shut it down the moment they knew. But pilots were dying. Mosquitoes were being shot down because they weren't quite fast enough. And here was a solution that worked. Channer asked only one question. Could it be done quietly? Banks said yes. It would take time. It would require discretion. But yes, the word discretion meant something different between them. It meant that Channer would look the other way. It meant that Banks would work at night. It meant that the station engineering officer would maintain plausible deniability. It meant that pilots who suspected what was happening would not ask directly and would not speak of it to anyone outside the squadron. It meant, in short, that they were all, collectively, breaking regulations they believed to be unjust in service of keeping men alive. The tactical situation in late 1942 was this. The Luftwaffe had superior numbers in its home airspace. The FW-190 had entered service in 1941, and by 1942 it was considered the finest single-engine fighter in Europe. The Bf-109G, with its newer engine and smoother airframe, was faster still at altitude. These aircraft were flown by pilots who were not militia. They were veterans of 3 years of continuous combat. They understood energy management. They understood that attacking was a choice, not an obligation. A Mosquito carrying a bomb load or on a reconnaissance mission was committed. It had to get to the target and back. That meant a predictable altitude band, a predictable route, a predictable airspeed. A fighter only had to reach that Mosquito once and hold it long enough to close range and shoot. The mathematics were brutal. A Mosquito at 280 miles per hour, carrying a 1,000-pound bomb, could not outrun an FW-190 at 350 miles per hour in a straight line, nor could it outclimb one at altitude. The only tactical option was speed in the form of surprise or altitude advantage or sheer distance. Attack before you're seen. Escape before you can be caught. Trust the design philosophy. So fast that interception is impossible. But impossible became difficult, became possible, as German fighter tactics improved. Coordinated pairs. Bounce from above. Hit and climb away. And crucially, experience. By late 1942, every German pilot in the Channel and over France knew that Mosquitoes were coming. They set up standing patrols. They anticipated vectors. They waited. In October 1942, a Mosquito from 105 Squadron failed to return from a daylight raid over occupied France. The pilot, Flight Lieutenant Walter Lees, had been on the run for several minutes before being caught near Amiens by a flight of FW-190s. His observer was killed instantly. Lees managed to bail out, but was captured. He would spend the rest of the war in a prisoner-of-war camp. In November, another was lost. Then another in December. 4 aircraft lost in 4 months. By March 1943, 105 Squadron had lost 7 Mosquitoes in combat. Some to engine failure. The engines were aging, pushed hard, not always maintained perfectly. Some to flak. Some to fighters. Pilots spoke in debriefs about German fighters that seemed to arrive at the exact moment they were vulnerable. None of them blamed the aircraft. The Mosquito was legendary. Any failure was their own, or their bad luck, or the attrition of war. But they went into the sky with an unspoken knowledge. The margin of safety had narrowed. The Air Ministry produced studies showing that medium bomber losses were within acceptable parameters. Acceptable parameters meant something like, if we lose 7% of our aircraft, it is strategically manageable. The pilots read those studies and understood that they were statistics. That 7% loss rate meant that if you flew 15 missions, the odds of your name appearing on a casualty list were roughly 50-50. Maybe better if you were lucky. Maybe worse if you weren't. Banks heard all of this. He heard it in the maintenance debriefs where pilots described the conditions they'd encountered. He heard it in the tension of ground crews who loved their aircraft and hated watching them come back shot to pieces or not come back at all. He heard it in the careful way that Wing Commander Channer never mentioned the modifications, but never prevented Banks from working late in the maintenance bay. And he accelerated his work. By spring of 1943, Banks had modified 8 aircraft. The pilots who flew them noticed immediately. One pilot, returning from a raid over occupied France, was surprised to discover that he'd been chased by a FW-190 for nearly 20 minutes and had simply climbed away. The German fighter had tried everything, climbing, diving, a sustained turn, but the Mosquito just kept pulling ahead. Eventually, the German pilot gave up and turned back toward the French coast. That pilot's name was not recorded officially in any report about engine modifications, but it was recorded in his logbook, and when he spoke to other pilots in the squadron, word spread. Word spread carefully, quietly, in the manner of dangerous secrets. A pilot from another squadron would mention casually to his ground crew that he wanted his aircraft to get the same treatment as the planes from 105. The ground crews understood. They would arrange for the aircraft to be available on a night when Banks was working. The modification would take 3 to 4 hours, adjusting the fuel jets, modifying the boost control mechanism, checking and rechecking the fuel mixture settings, testing on a stand to ensure everything held. By summer of 1943, Banks had a network. Fitters at RAF Marham, yes, but also at other stations. Other engineers who understood the principle, who had the skill, who had the moral conviction that pilots' lives mattered more than Air Ministry regulations. They called it, between themselves, the Shadow Modification Network. No paperwork, no official record, just the quiet word-of-mouth spread of innovation, moving through the RAF like an infection. The speed gains were modest by specification, 15 to 30 miles per hour, depending on the engine condition and the pilot's technique. But in the context of aerial combat, 20 extra miles per hour was the difference between escape and capture, between home and captivity, between a name on a roster and a name on a memorial. In late 1943, Banks was transferred to RAF Banff in Scotland, a station that had just received Mosquitoes for anti-shipping strikes. The climate was harsh. The runway was short. But the pilots were good, and they were flying dangerous missions against German vessels in the North Sea and Norwegian fjords. Banks arrived with his notebooks. He arrived with a reputation that had spread quietly through RAF Bomber Command. Within a week, pilots were requesting him by name. The Rolls-Royce Merlin was AV-12 liquid-cooled engine, 27 liters of displacement, capable of producing 1,500 horsepower at full throttle. It was one of the finest aero engines ever built. Also, like all machines designed by human beings, it had margins. Explicit margins, tested margins, but margins nonetheless. The engine's supercharger, the mechanical compressor that forced air into the cylinders, increasing oxygen density and thus the weight of fuel mixture that could be burned, was governed by a boost control mechanism. This mechanism adjusted intake pressure automatically, preventing the manifold pressure from exceeding the official limit. For the Merlin, that official limit was, during normal operations, around 15 pounds per square inch of manifold pressure. At this setting, The engine would produce approximately 1,315 horsepower and could operate indefinitely. There was, however, a war emergency power setting that allowed for 20 to 25 pounds of boost for limited periods, typically no more than 5 minutes for emergency climbs or evasion. At war emergency, power output jumped to approximately 1,475 horsepower, and engine life was significantly shortened. Banks' insight was simple but revolutionary. The gap between normal operations and war emergency was itself a gap that could be safely occupied for limited durations. What if an engine could run at 18 pounds of boost? Not maximum war emergency, but not normal operations either. What would happen? Mathematical answer. The engine would produce approximately 1,385 horsepower, a modest increase of 70 horsepower, which would translate to a speed increase of roughly 20 to 25 miles per hour. The stress on the engine would be elevated but not catastrophic. The engine would require more frequent overhauls, perhaps 25 hours less of normal service life. But an engine at the end of its service life anyway wouldn't suffer from abbreviated service. What Banks did was physically adjust the boost control mechanism to prevent it from achieving the official limit. He would file down certain components or adjust linkages so that the engine, under full throttle, would reach 18 or even 19 pounds of boost instead of settling back to 15 pounds. He would modify fuel jets to supply the richer mixture that the higher boost would require. He would test and retest and document everything in his private notebook. The modifications were reversible. If an engine were to be inspected by Rolls-Royce or the Air Ministry, Banks could restore the original settings in approximately 20 minutes. But by the time any such inspection was likely to occur, the engine would have already done its work. A Mosquito with a modified Merlin would have flown its mission, come back, and been re-refueled for the next operation. The critical flight, the mission where the extra 20 miles per hour made the difference, would be long past. Banks would perform the modifications late at night, after duty officers had finished their rounds. He worked alone, usually, or with one trusted fitter. The work required precision. One mistake, an improperly adjusted fuel jet, an incorrectly filed component, could cause detonation, catastrophic engine failure. The failure would come at 18,000 feet. It would come suddenly. The engine would come apart from the inside, metal fragments tearing through the firewall, oil spraying across the fuselage, the aircraft suddenly in an uncontrollable dive. 2 men in the cockpit. 2 seconds to react. The ground below. Banks did not make mistakes. His hands were exact. His measurements were exact. His calculations were exact. In 3 years of modifications, across dozens of aircraft, across a network of fitters he trained personally, there was only one catastrophic engine failure that could be traced to the modifications. That failure occurred in late 1944 when a fitter at a different station, less experienced, less careful, made an adjustment incorrectly. The engine failed over occupied territory, and the aircraft went down. Banks was not present for that failure, but he heard about it. He kept detailed personal records of every modification, every engine, every flight. When he learned of the failure, he took additional precautions. He required that the fitters in his network be personally trained. He monitored fuel flow more carefully. He began keeping a coded logbook tracking each modification and its history. The pressure on Banks was immense. If discovered, the modifications were sabotage. Not intentional sabotage. The intent was to save lives, but sabotage nonetheless. Unauthorized modifications to military aircraft. Violation of Air Ministry directives. Violation of Rolls-Royce specifications. A court-martial offense. Prison time. The end of his career and reputation. The pressure on the fitters in his network was equally immense. They were all complicit. They were all, in a sense, waiting for discovery. The psychological toll was significant. Several suffered from what would now be recognized as severe stress symptoms. One developed a tremor in his hands. Another reported insomnia lasting weeks at a time. They were keeping a secret that, if revealed, would destroy them. They were breaking rules they had been trained to follow absolutely. And they were doing it because pilots' lives mattered more. Roderick Banks never spoke about the pressure publicly. But decades later, in interviews, he acknowledged it simply. The stress, he said, was not theoretical. The possibility of discovery was real. The consequences were severe. But the alternative, Maintaining the fiction that bureaucratic regulations mattered more than human survival was, to him, unthinkable. The moment of truth came not from a combat mission or a dramatic escape. It came from Operation Jericho on February 18, 1944. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The target was Amiens prison in occupied France. The French resistance had requested that British bombers destroy the prison's walls to allow French prisoners, many of them resistance members, to escape. It was a precision strike of extraordinary difficulty. The prison was surrounded by a town. The bombs had to hit the walls without destroying the interior buildings where prisoners were held. The margin of error was measured in meters. The RAF assigned the mission to a special formation of Mosquitoes from 2 Group, Bomber Command. Low-level strike, broad daylight, over occupied territory, defended by German fighters and flak. The Mosquito was the only aircraft that could perform the mission. The speed, the precision bombing capability, the maneuverability. Only the Mosquito could do it. And only if every aircraft in the formation maintained formation integrity while moving at near-ground level at 350+ miles per hour. All of the Mosquitoes selected for Operation Jericho received Banks modifications. Every engine in every aircraft had been adjusted. Every boost control had been filed and refined. Every fuel jet had been modified. The formation crossed the channel in bright daylight. They were spotted by German radar. Fighters were scrambled. FW-190s and BF-109s climbed to intercept. But the Mosquitoes were fast. Faster than they were supposed to be. Fast enough that the German fighters could not close range. Fast enough that the formation could complete the bombing run and depart before a coordinated interception could develop. The bombing was extraordinarily accurate. The prison walls were destroyed, 102 prisoners escaped, and all but one of the Mosquitoes returned safely. The one that didn't return was shot down by an anti-aircraft shell, not by a fighter. It was not an engine failure. The modified engines had performed flawlessly. Word of Operation Jericho spread through RAF Bomber Command within days. The modified Mosquitoes had completed a mission that was supposed to be barely survivable. The pilots credited the aircraft's speed. The ground crews knew better. The modifications had provided exactly the margin, 20 miles per hour, that allowed the formation to escape and complete its mission. But officially, nothing was said. It was at this point that Ernest Hives, the chief engineer of Rolls-Royce, decided to investigate. Hives was brilliant, methodical, and ultimately practical. He had heard rumors of tuned Mosquitoes. He had seen performance data that didn't match specifications. He had listened to pilots talk, carefully, about aircraft that were faster than they should be. In February of 1945, Hives arrived unannounced at RAF Marham. He found Roderick Banks in a maintenance hangar, elbow deep in an engine, adjusting a fuel jet with surgical precision. Banks had no warning. The visit was unscheduled. For a moment, everything hung in the balance. This was the moment of discovery. Hives watched Banks work. He watched the precision. He listened as Banks explained, matter-of-factly, exactly what he was doing and why. He examined Banks' personal logbooks and test notes. He studied the modifications. He asked technical questions. Banks answered each one with the calm exactitude of an engineer explaining established fact. Hives did not order Banks to stop. He did not report him to the Air Ministry. Instead, Hives did something extraordinary. He said, "This is good work, Banks. Solid engineering. But if you're going to keep doing it, you need to do it properly." Hives began supervising the modifications personally. He helped refine them. He brought in Rolls-Royce resources to validate the work scientifically. Instead of being suppressed, the modifications were brought into the light. Not officially, still not by Air Ministry directive, but under the aegis of Rolls-Royce's chief engineer, essentially legitimizing the work even while maintaining the fiction that it remained unofficial. By spring of 1945, the modifications were no longer a shadow network. They were a managed program. Every Mosquito in RAF service could receive the modifications if the crew requested it. Other units, other squadrons, began implementing versions of the techniques Banks had pioneered. The performance data was striking. Squadrons with modified Mosquitoes reported measurably lower loss rates. One squadron operating modified Mosquitoes over occupied France reported a loss rate of 2.1% over a period of 6 months. Standard Mosquito squadrons operating in similar conditions reported loss rates of 4.7%. The difference was not enormous, but it represented dozens of lives. Dozens of pilots and observers who came home instead of becoming statistics in a casualty report. Captured German pilots, in post-war interrogations, commented on Mosquito performance. They said the aircraft had become faster as the war progressed. They said that by 1945, German fighters had essentially given up attempting to intercept Mosquitoes in level flight. The speed advantage was too great. The best tactic was to catch them in the climb out from a target or in a vulnerable moment. Otherwise, the Mosquito simply outran pursuit. None of them knew about Banks' modifications. They assumed the speed gain came from new aircraft models or improved engines from Rolls-Royce. The truth, that a sergeant fitter with precise hands and a conviction about what was right, remained classified. Roderick Banks was not awarded a medal. His name does not appear in official histories of the Mosquito. No citation mentions his contributions. The modification network he built was never formally acknowledged. After the war, he continued his aviation career, eventually retiring as an air commodore. But even then, the details of his wartime work remained largely obscure. But the fingerprints were everywhere. The principle that Banks established, that engines could be safely operated at higher boost pressures for limited durations, became standard doctrine in jet engine development. The Rolls-Royce engineers who worked with him after 1945 incorporated those insights into the development of the Avon and other jet engines. The understanding that margins can be safely pushed, that specification limits are not walls but thresholds, informed a generation of engine development. The modification network itself, the informal dissemination of technical knowledge through practical channels rather than official documentation, became a model that was replicated throughout the RAF after the war. Ground crews began to be seen not as maintainers of official specifications, but as innovators and problem solvers. The idea that a sergeant fitter might understand something about an engine that an Air Ministry regulation had not yet caught up to became, gradually, accepted practice. After the war, Banks wrote papers on aero engine development. He advised on the design of new fighters. He became, without fanfare, one of the most influential figures in British aviation engineering during the Cold War. But he rarely spoke about the Mosquito modifications. When asked directly, he would confirm the basic facts. He had made adjustments. They had worked. Pilots had benefited. He did not elaborate. He did not claim credit. He simply stated the truth and moved on. In one interview from the 1960s, a historian asked Banks whether he had ever regretted breaking Air Ministry regulations. Banks paused. He thought for a moment. Then he said, "Regulations are written by people who are not in the cockpit when the enemy is shooting. I was in the hangar when the pilots came back alive. The regulation was wrong. The pilots mattered more." The Mosquito itself went out of service in the late 1940s, replaced by faster jets. But the principle endured. Every fighter pilot who flew high-altitude interception missions during the Cold War, every bomber pilot who maintained aggressive climb rates, was operating under the assumption that engines could be pushed beyond official specifications in moments of tactical necessity. Banks had made that assumption valid. The exact number of lives saved by the modifications is impossible to calculate. How do you count the aircraft that didn't crash? How do you count the pilots who came home because they were fast enough? One historian estimates, based on loss rate analysis, that the modifications directly resulted in the survival of dozens of aircraft and the preservation of over 100 crew members. Others argue the number is higher, but the mathematical certainty is impossible. What is certain is this: when Operation Jericho succeeded, when the prison walls came down and prisoners escaped, the modified Mosquitoes played a critical role. A mission that had been officially rated as barely survivable was executed with only one loss. The difference between bare survival and actual success was speed. The speed came from Banks' modifications. Operation Jericho is now a legendary moment in RAF history. It is cited as an example of how precision and courage can overcome impossible odds. But the role of the engine modifications is often omitted from the narrative. The focus falls on the pilots, on the precision bombing, on the audacity of a low-level daylight strike over occupied territory. The ground crew is a footnote. Banks accepted this. He understood that pilots carried the weight of combat, that their names belonged on the monuments and in the history books. He had no need for recognition. He had the satisfaction of a man who had solved a problem through precise thinking and had seen the solution work. In his final years, Banks occasionally attended RAF reunions. Mosquito pilots would approach him, often not knowing who he was. They would talk about specific missions. They would describe aircraft that seemed faster than they should have been. Banks would listen. He would ask questions about the flight characteristics, about the outcome of the mission. He would never volunteer information about his role. One pilot, who had flown modified Mosquitoes in 1944 to 1945, wrote a letter to a RAF aviation magazine describing a close encounter with a German fighter. The pilot had been chased at low level for nearly an hour and had simply climbed away, the Mosquito pulling up and away in a way that the German fighter could not match. The pilot had wondered, at the time, why his aircraft seemed faster than its specifications. Decades later, he learned about Banks' modifications. He wrote the letter to acknowledge the debt. Banks received letters like this throughout his life. He kept them, filed carefully, but never responded to them publicly. The information was for his records, he said, a reminder of what had been accomplished. He died in 1978. His obituary mentioned his service as an RAF engineer. It did not mention the Mosquito modifications. It did not mention Operation Jericho or the pilots who came home because his engines were faster than they were supposed to be. But in aviation engineering circles, the loss was understood as significant. The question that historians have struggled with since is, how could such an important contribution remain so obscure? The answer involves several factors. The modifications were, technically, violations of Air Ministry regulations. Even after the war, when the regulations were no longer operationally relevant, acknowledging them officially would have required admitting that the Air Ministry's specifications had been suboptimal. The military is not inclined to make such admissions. Second, Banks was not a pilot. Wartime narratives and post-war histories tend to focus on the men in the cockpit, not the men in the hangar. Pilots are visible. They are photographed. They are interviewed. Ground crews are assumed, taken for granted, acknowledged in general terms, but rarely honored specifically. Third, Banks himself resisted publicity. He understood that modesty and discretion were not just personality traits, but survival skills in a military bureaucracy. Drawing attention to the modifications could have drawn inspection and censure, even years later. The safer course was to let the work speak for itself, in the form of aircraft performance and pilot survival, and to never call attention to the man behind it. But perhaps most importantly, the modification network had done its work so effectively that it had become invisible. The Mosquito's reputation for speed and performance was so well established that everyone assumed it was a function of the aircraft's design. No one outside the RAF's maintenance units needed to know that the speed advantage had been achieved, in significant part, through careful engineering by men whose names were never recorded. The physics underlying Banks' modifications deserve closer examination because they illustrate a principle that remains relevant in engineering today: the difference between specification limits and actual failure points. A piston engine's maximum output is constrained by several factors. The first is thermodynamic, the amount of fuel that can be burned in the combustion chamber per power stroke. The second is mechanical, the stresses that the engine's materials can withstand. The third is practical, the detonation point, where the fuel-air mixture ignites prematurely rather than in a controlled fashion. Rolls-Royce designed the Merlin to achieve its official maximum power output with a significant safety margin. If an engine operating at 15 pounds of manifold pressure could do so for 200 hours without failure, the engineers were confident in that rating. But that rating included allowances for manufacturing tolerances, for variations in fuel quality, for unforeseen mechanical issues. A perfectly built engine, in perfect conditions, with perfect fuel, could potentially operate at higher pressures. The question was, how much higher? Banks approached this scientifically. He started with known parameters: the engine's displacement, the compression ratio, the fuel's octane rating, the material's stress limits. He calculated, mathematically, what additional boost pressure the engine could theoretically withstand. Then he tested those calculations on actual engines, instrumenting them with gauges to monitor cylinder pressure, exhaust temperature, and detonation knock. The results confirmed his theory. A Merlin could safely operate at 18 to 19 pounds of boost for the durations typical of combat flying, usually 1 to 2 hours per mission, without exceeding the stress limits of its critical components. The penalty was accelerated wear on piston rings and valve seats, reducing total engine life by perhaps 10 to 15%. But an engine that had already accumulated 150 hours of service and had perhaps 50 hours remaining anyway would not suffer appreciably from that reduction. The efficiency gain was modest. Approximately 5.5% more power output translated to approximately 5 to 6% higher cruise speed, or roughly 18 to 24 miles per hour on a Mosquito flying at 380 miles per hour baseline. In absolute terms, that is a small number. But in the context of air-to-air pursuit, it is significant. The physics of pursuit dictate that a faster aircraft can overtake a slower one, can extend range, can disengage from an engagement that is not advantageous. A 20-mile-per-hour advantage, sustained over the duration of a chase, translates to increasing distance. A pursuer who cannot close range can eventually be evaded. German fighter pilots understood this. By 1944, the standard tactic against Mosquitoes was not to pursue in level flight. The Mosquito would simply outrun the fighter, but to attack when the Mosquito was vulnerable. In the climb out from a target, when it was slow and heavy. In the descent to low level, when it was committed to a specific flight path. Banks' modifications did not solve the problem of vulnerability. They only improved the margin of escape when a tactical opportunity presented itself. But in combat, margins are measured in meters and seconds. A 20-mile-per-hour advantage is the difference between escape and capture, between survival and death. Why did the Air Ministry not simply increase the Merlin's official boost limits? The answer is instructive for understanding how institutions function, especially military institutions. First, there is the principle of conservatism. An Air Ministry specification is not just an engineering statement. It is a contractual obligation. Rolls-Royce designed and warranted the Merlin at certain power limits. If the Air Ministry increased those limits, they would be implicitly stating that Rolls-Royce's original specifications were inadequate. This would create liability questions, questions about what else might be inadequate, questions that propagate through the supply chain and the bureaucracy. Second, there is standardization. The Merlin was installed in multiple aircraft types: Spitfires, Lancasters, Hurricanes. If the Air Ministry increased boost limits for Mosquitoes, would they also increase them for bombers? Would they increase them for fighters? Each aircraft had different operational profiles, different stress regimes. Creating non-uniform specifications would have created a nightmare of maintenance and tracking. Third, and most importantly, there is the problem of knowing what you do not know. Engineers at Rolls-Royce and the Air Ministry had designed the Merlin based on extensive testing and conservative assumptions. They did not know with certainty what the maximum safe operating pressure was. They knew a safe pressure, 15 pounds of manifold pressure, and they included a margin of safety above that. To increase that pressure would require knowing that the margin was sufficient, which requires testing, which requires time. Banks had the advantage of working at the margins, testing individual engines to destruction, allowing one engine to fail so that he could understand where the limits actually were. The Air Ministry did not have that luxury. Or rather, it had the luxury, but the cost was uncertainty and the possibility of catastrophic failure on a large scale. So the Air Ministry chose conservatism. It chose the known safe operating point rather than the theoretically possible operating point. Banks chose differently. He traded the safety of institutional certainty for the practical risk of specific failures, knowing that the specific failures would be localized, one aircraft, one engine, while the institutional certainty was costing dozens of aircraft and hundreds of lives. This is the eternal tension in military organizations, the tension between following the rules and breaking them for practical necessity. Banks resolved it by breaking the rules carefully, testing systematically, and accepting the personal risk that came from being discovered. His judgment proved correct. The modifications worked. They saved lives. They were eventually validated by Rolls-Royce. But what if they had not worked? What if a modified Mosquito had experienced catastrophic engine failure over the channel? What if pilots had died? Banks would have been court-martialed. He would have been the villain, the renegade fitter who violated regulations and got people killed. the story would have been told very differently. History judges outcomes. It judges winners. Banks won. The pilots came home. The modifications were validated. So he is remembered as a brilliant engineer, not as an insubordinate troublemaker. But the judgment could easily have gone the other way. After the war, Roderick Banks continued working in aviation. He held a commission in the RAF and advised on engine development for the transition to jet propulsion. He was respected in engineering circles, though his work remained somewhat obscure to the public. In the 1950s and 1960s, he served as a technical advisor to aircraft manufacturers and the RAF. He was consulted on engine problems and performance optimization. The lessons he had learned during the war, that careful engineering could extract margins from specifications, that risk could be managed through systematic testing, that bureaucratic regulations were not inherently correct, informed his post-war work. But he never again operated outside the official system. He never again broke regulations. What changed was not his engineering philosophy, but his position. Once he had authority, he did not need to defy authority. He could simply ask for modifications to be made through official channels, and they were made. In his later years, Banks was invited to speak at engineering conferences. He would discuss aero engine development in general terms. He would talk about the evolution from piston to jet propulsion, about the challenges of materials and combustion dynamics, about the importance of thinking deeply about problems rather than accepting surface explanations. He would rarely mention the Mosquito modifications directly, but the engineers in his audiences understood what he was saying. The lesson was, question the specifications. Test the margins. Do not accept bureaucratic answers to engineering problems, but test carefully. Document thoroughly. Accept the consequences of being wrong. One of the fitters who worked with Banks in the modification network, a man named Winters, attended a reunion in the 1970s and was asked by a younger engineer about the modifications. Winters explained the process, the care that Banks had taken, the systematic approach to pushing the margins. The younger engineer asked, "But weren't you afraid of being caught?" Winters answered, "Of course, every single night. But the alternative was worse. Accepting that regulation mattered more than lives. Once you've made that choice, the fear becomes manageable." Roderick Banks died in 1978. He had lived to see the Merlin engines phased out, replaced by Rolls-Royce Avons and Merlin's successors in jet form. He had seen aviation technology transform from piston to turbine to supersonic flight. He had seen the principles he had tested on Mosquito engines inform the design of the most advanced aircraft in the world. The Mosquito was retired from service by the early 1950s, replaced by faster jet bombers. In a sense, the aircraft was obsolete before the war had even ended. Newer designs were already drawing on the lessons of the Mosquito's success. But the principle that the aircraft represented, that speed was the ultimate defense, that careful engineering could exceed expectations, remained. Every jet engine that operated at boost pressures higher than the baseline design specification, every aircraft that achieved performance beyond its official ratings, carried in some small way the fingerprints of the work that Banks had pioneered. The story of Roderick Banks is a story about the tension between institution and individual, between rules and judgment, between safety and necessity. It is also a story about invisibility. The most consequential innovations in war often come not from the men in the cockpit, but from the men on the ground. Not from the pilot who flew the mission, but from the fitter who tuned the engine. Not from the commander who ordered the raid, but from the engineer who calculated whether the aircraft could actually do it. These stories are hard to tell because they lack the drama of combat. They lack the visible heroism of a man fighting in the sky. They are stories about precision and patience and the willingness to accept risk for the sake of something larger than yourself. But they matter. They matter because they show how wars are actually won. Not by single moments of genius, but by thousands of small decisions made by people whose names no one remembers. People who see a problem, understand it deeply, solve it carefully, and move on. Roderick Banks did that. He saw mosquitoes dying because they were not quite fast enough. He understood the physics of why. He solved the problem with precision and care. He accepted the risk that came with breaking regulations. He was vindicated by the results. His name is not on a monument. It is not in the official histories. Most people have never heard of him. But every time an engineer questions a specification, every time an innovator pushes the margins, Every time someone decides that institutional rules matter less than human survival, they are following the path that Banks cleared. Some legacies are carved in stone. Others are written in engines, in the differential between what regulations say is possible and what careful hands can actually achieve. Roderick Banks' legacy is in the latter category. He died believing, knowing, that he had done good work, that pilots had come home because of his precision, that his judgment had been sound, even when it violated the judgment of institutions, that the rules were sometimes wrong, and that breaking them carefully could save lives. In a war where hundreds of thousands of men died for causes that were not always clear, where bureaucracy and glory competed for the authority to decide who lived and who died, Roderick Banks chose the side of the pilots. He chose precision. He chose risk. He chose human judgment over institutional regulation. And he was right. If this history matters to you, tap like and subscribe so these stories of the people behind the machines aren't forgotten. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.